All right, so welcome everyone. Thanks a lot for joining us today in our first webinar. We will today speak about computer vision and artificial intelligence in industry applications. With me today are the CEO of Assaia, Mr. Max Dietz, the CTO of Assaia, Dr. Nikolay Kobyshev.
Hey everyone.
And the senior researcher from the ETH Zurich in the computer vision lab, Dr. Radu Timofte. My name is Jan-Willem Kappes and I'm the Director Business Development EMEA and APAC at Assaia. And today we will basically cover the following agenda. So Max will start with a brief introduction about today's webinar and also about the company Assaia, followed by Nikolay, who will present about the science behind AI, the industry applications of computer vision and AI. He will also give some further examples where this topic is becoming more interesting, and he will close with a future outlook about the trends that will happen within the next couple of months and years. And we will follow and we will end this session with a Q&A where you can ask questions. There is a question functionality at Zoom. It's called question and answers. So basically over there you can already during the presentation post questions that we will then answer at the end of the presentation. So in between, we will not directly answer any questions, but at the end we will come back to you. All right, and with this, I'm happy to hand over to Max.
Thank you so much, Jan-Willem, and thank you for the introduction. Very warm welcome from my end as well. So even though it's like we heard a lot of, director business development, Assaia, CEO, the idea of this is not to be an infomercial or so, but the idea is to spark a few thoughts in your minds, with regards to AI. So I'm gonna very briefly talk about one aspect in terms of how I think people should think about configuring their AI activities from a strategic or business point of view. And then Nikolay will go into more details on really the main thing. One forward, please. Thank you. So very briefly about us, we're a startup based out of Zurich, and we're a team of around 35 fantastic people with whom I'm really blessed to work with. Most of us are working on the technical end. And the only application or solution that we're currently providing is what we call the Apron AI. So Nikolay will give a very quick demo. And this is really as AI heavy as an application can get these days, and from my point of view. So what we see here is a computer vision algorithm that's based on machine learning that detects different signals in a real-time video stream, translates this into structured data. And as we'll see, we consider this part as one fundamental building block of industrial AI, which is essentially this computer vision building block. Okay, can we switch back into the next slide?
Yes.
Thank you.
Just take a second. Just to make sure you don't. Okay, now you should see.
Fantastic. So as I mentioned, one of the sparks that I wanted to trigger in your mind is how should we configure a business, against the 10x change that AI is. And one of my favorite business books is Only the Paranoid Survive by Andy Grove, who was long time chairman of Intel Corporation. And he's in this book, he's talking about how Intel managed the successful transition from manufacturing and selling memory chips into manufacturing and selling CPUs, which was a huge change. And actually the existence of Intel was in question back at that time. So if we can go one step further. So what Andy Grove had observed was happening in the computing industry was that a 10x change had happened in terms of manufacturing technology. And while in the 1980s, the computer industry was verticalized. So there was IBM, would do everything themselves, build their own chips, put them in their own mainframes, do the sales and distribution, and then the support as well. And within 10 to 15 years, the entire industry was changed. It went into a very horizontalized business industry, where in every horizontal layer, huge economies of scale would get to work and would allow, for example, significant decreases in chip prices. Why I'm saying this, it's always difficult and dangerous to reason by analogy, right? But what I want to spark in your mind is essentially this thought is, how should we actually set ourselves up with regards to AI? As a consulting business or a software company, or an airport, for example, or an industrial manufacturer. And we have some thoughts into which we put in a lot of consideration, really. So what we're seeing is we are obviously decoupled in terms of the infrastructure that we're using, right? We're running in the cloud, even though we're also using a separate training cluster that we own. And apart from that, most of the stuff is really integrated. And we really believe that a high level of integration will allow customers to really derive the value from the AI application. Deriving value from the application, how we can achieve that, I think that's a good question that Nikolay will pick up in the next few minutes.
Cool. Thank you very much, Max, for the intro. I think we can go directly to the technical side. So there will be, of course, no very technical introduction to AI, but I think it's still worth spending a couple of slides just to bring us to the same level of understanding. So essentially, as Max has already mentioned, AI is getting much more important than it ever was in the whole area of computer science. And the first question one might wonder is, why is that the case? And why is that something which is expected to make the industry 10 times larger, more efficient, or larger? So here is a couple of examples which computers are perfectly capable of solving without any AI. To the left, you see the routing task. So you see there is a Google Maps which managed to compute an optimal route in terms of speed from Zurich to St. Petersburg within the microseconds. And this is really the best route you can get. To the right, you see the 3D rendering of a scene which looks almost indistinguishable from a photograph. So this is amazing. This is just fantastic examples of how computers can be helpful. And this is done completely without AI. So what actually makes AI so interesting, and why is it actually important? So the deal is the problems I have just shown, as well as very many other problems, are so-called classical computer science problems, and their property is that we essentially know how to solve them. So for example, for routing, we have the algorithm, we know the steps, and if you take the steps 1,000 or 1,000,000 times, you end up with your perfect routing. With the 3D models is the same. You know how light transfers, you know the properties of reflectance of different surfaces. So essentially the only thing you need is you need some computational engine to model your simulation. And this is what computers have been amazingly good at for the last 50 years. But the thing is that unfortunately the set of such problems is very limited, and it would be safe to say that almost all of them are almost solved currently with computers. But there is a lot of other problems which are not solved with computers yet. And this is exactly where AI comes. So I'm not talking about some deeply philosophical questions like the purpose of life and the meaning of universe. I'm talking about problems which actually for sure have a solution. It's just we don't know how to teach computers get these solutions. A very classical example, I think you have seen it already, but it's very important, is this task. You have two pictures of animals, and your task is to say which one is a cat, which one is a dog. It's extremely simple for any human to do this task. Of course, the left one is a cat, the right one is a dog, but it's not exactly obvious how would you explain to, for example, a computer on how to define a cat as opposed to defining a dog. So you could say that the cat is like smaller than the dog, but that's obviously not the case. You can say that a cat is maybe more fluffy than a dog, but it's also not always the case. So the deal is it's extremely hard to find a fixed set of rules following which the computer will be able to identify is it a cat and is it a dog. I have to switch from this slide because it's too ugly. Good. So the deal here is as follows. We don't know how to solve the problem, but we know the machinery which solves this problem. So in this case, just to limit the AI to deep learning, we know that this problem of recognizing a cat and distinguishing it from the dog is solved with a human brain. So why not model a human brain in a very simple way? So we all know that information flows through our retina and reaches our visual cortex where the decisions are taken, and it goes through a bunch of neurons, and then it's interwired within the visual cortex as well. So the idea of AI and deep learning in this particular case is very, very straightforward. You just make a little simulation of this system, which is the brain in this case, and see if it solves the problem or not. And as you obviously all know, it does solve the problem very, very, very well. So, okay, you have your brain. The next problem is you need to teach this brain. Obviously, if you have a child infant, which has a very capable brain, this infant is still not capable of distinguishing cats from dogs because they essentially never seen ones. So you need to expose the system to the training data. And this is, I think, the story of AI that everyone has heard already. You really need a lot of training data and properly structured training data. So just to recap on that, what is the training data? So the training data is essentially, at least in the field of computer vision, is a set of images which represent the task you're trying to solve, paired with the solutions to this task. So in the simplest case, like we've discussed before, you just have a bunch of images and you want to detect what is happening in this image. So if you look at the left side of the slide, you see exactly that. You see a bunch of images of animals, but they're separated with this line between cats and dogs. So it's very, very easy. So it's actually a very, very good training set, because you can teach AI a picture and you say, this is a cat or this is a dog. And then you just repeat it a lot of times. So to say that from the beginning, usually to train a system from scratch, you would prefer having something around thousands or even millions of images. So of course, it doesn't have to be as simple as cats and dogs. You can use it for something more useful. For example, instead of cats and dogs, you can give the MRI scans of tumors, and the system will have to say if it's benign or malign. Or if you don't go to medical application, you can do something as simple as detecting human emotions. You show photographs of people, and you want to detect if the person is happy or not happy, which has quite a lot of business application, the main of which, of course, is doing targeted marketing, because you know how people feel about your product. So this is about the very standard data when you just give classes to images. You don't have to do that. For example, in very many applications, you need to localize images and localize objects in your images and get the approximate size. So this is what's happening in the middle case. Here we have the I think it's foxes. The fox is highlighted. So this is the data set for training a fox detector. But this is, of course, maybe not the case with the most money in it. If you imagine the case with more money, you would maybe think of understanding the objects on the roads. For example, you want to build a speed cam that detects cars that are speeding. So you actually need to understand how this car is moving. Or you want to count people in queues to understand how large your queue is. So these are some of the classical applications of object detector. If you put this idea on steroids, you get to semantic segmentation, which is depicted to the right. In this case, for every pixel of an image, you want to detect which type of object it is. So for example, in this case, the cars are blue, the traffic lights are yellow, and so on. People are red. So this is needed in the most obvious example of self-driving, for example, where you really, really need to know what's happening around you to take a proper decision. But also some more playful examples include video background segmentation. So you see my face now, and for example, you want to replace my background with some background picture. We all know we can do it in Zoom. So for that, you actually solve exactly this problem. You identify for every pixel in my face whether it's actually the face or it's already the background. So this is like classical input for classical computer vision tasks. So this is examples of data. So once you have this data and once you have this system, it doesn't take too long with the current tooling to train the system. So essentially, on the very simplified level, having enough of data which is relevant to solving your problem is already enough to train an AI system. So what do you mean? What do I mean by having a trained AI system? Well, I simply mean that if you have a trained AI system, you can give it the new data, and it will create you a new label. So, for example, you train your system on 1 million of images of cats and dogs, and then you show it a new image of an animal that it has never seen before, and the system will automatically identify with certain probability if it's a cat and dog or if it's a dog. And as we know, the simple cases are completely solved already. More difficult cases, the systems are still not perfect, but we're very steadily getting there. So one note I wanted to say on that, this step, which is called inference, when the system already works and produces new results, at this point, the system does not improve on its own. So this is a common misconception. People think that, okay, because the AI is similar to human brain and I show the tendency of learning all the time, maybe the system will do the same. No, unfortunately it doesn't. So if you have deployed your AI system somewhere, you actually have quite an overhead of maintenance there, because at very least what you want to do is to run some continuous tests which repeat every month or several months to make sure that your system's performance does not deteriorate. And unfortunately, if it deteriorates, the only way of getting out of this not very nice situation is to train it further. So you have to collect a further data set and repeat the original training. So unfortunately, the system will not continue just working, and the system also is not capable of improving its own without any external assistance. So this is really a very, very, very brief overview of the concept of machine learning. So you have your training data, you have your black box, which somehow manages to learn to get your task. Yeah, I think that's actually it. Maybe Jan-Willem, you would summarize the main takeaways so that someone external does it and not me all the time.
Thank you, Nikolay. Yes. So I think the key takeaways from what Nikolay just told us is that there's one key bottleneck, and that is that AI training requires a lot of annotated data. So what can you do if there is not sufficient data? That's the problem, and then it is hard to do it.
Well, we will show later that there is a lot of attempts to solve it, which are pretty successful. But in general, yeah, that still holds, unfortunately.
Yes. And traditional AI systems are not self-improving. As Nikolay said, I think that is a very common misunderstanding, that as soon as someone hears AI nowadays, she or he thinks that this is automatically self-improving, but that is unfortunately not yet the case, and there's still a huge maintenance effort required.
Yeah, and the last point I wanted to take from that is that we know that machine learning is great, but there is a tendency of over-engineering and solving everything with machine learning, which essentially is not a good tendency. So even if computer vision is considered as an example, so just imagine you have your quality analysis system, which has to understand if the screws you provide are of the defined length, for example, of 10 centimeters or not. So if you have some kind of computer vision system which just gives you a silhouette of the screw, which is white on the foreground and black on the background, so essentially you see your screw there, there is no need to use AI or any kind of machine learning to measure the length of your screw, because you can just count the amount of pixels, and that will work much easier and with the same reliability as an AI system. So there is a ton of tendency of making, so people generally tend to overkill this task and use machine learning for everything. But the reality is that you really would like to apply some expertise in the beginning and understand whether this task requires machine learning approach or a classical approach will work better and be much more efficient and cheap. Good. Let's go to the next chapter, industry applications of computer vision and AI. And here I wanted to bring a little bit of a paradigm. So almost any industrial application or almost every industrial system consists of three components: data acquisition, analysis, and decision. And it doesn't matter if it is equipped with the latest technology and is done with computers, or is it done by humans. This is just how all the systems work. For example, if you have a factory, you need to produce a certain amount of pieces a day. So first you have a set of machines. So first you need to understand how your machines work. What is, for example, the throughput of each machine? What is the queue in front of each machine? What is the fail rate of each machine? You can understand it just by analyzing, just by talking to the machinist, but maybe you have some kind of fancy IoT system which generates this data for you. Then, once you have this data, you can do analysis. So analysis essentially in this case is maybe to understand what is the bottleneck in your chain, which machine you need to replace, or maybe you need to buy a second one to improve your capacity. And the third decision, and the third part of the pipeline is actually taking a decision. So with the analysis made, you actually say, okay, I have a bottleneck. Now my decision is to buy another machine. And then this influences your data, and then the whole thing starts again. So this is a very abstract level because it applies to almost any system, be it a business system or engineering system. And the example, the very close to my heart example where we work is essentially the aviation industry. So there is a lot of different things you can do in aviation, but what we at Assaia are doing is trying to help airports become more efficient in terms of utilization of their gates. So the meta problem that airports want to solve is to make gate optimization, gate allocation more efficient, so that when the plane arrives, it is directed to the right gate so it can leave on time. So this maximizes a lot of different KPIs, beginning with the on-time performance of the planes, but also something like optimal use of buses, optimal use of tugs, and all these little things that exist in the aviation. So to be able to, we're going from the right to the left in this plot, and actually I think it's better to go to this one. So you want to do the optimization. This is the rightmost thing. So to do optimization, the thing you really need to have is to have some visibility into the future. So you want to say this plane will leave at this time, and this plane will leave at this time, because only having this information, you can actually properly allocate the future arriving planes to the gates which are still occupied. So currently this predictive analytics is done by humans. There is essentially a person who puts some special timestamp saying, I assume that this plane will leave at this time. It is needless to say that this is not the most efficient way of doing that, because humans are not really good. So first of all, humans are not really good at performing tasks very diligently. So sometimes people just put some random information to the system, which potentially leads to a very erroneous decision in the future. But also humans just are by design not the best mechanisms for giving good predictions for the future. So you would prefer replacing humans with some algorithm which just looks at what happens to the turnaround. For example, when the fueler comes, when the catering comes, when the jetty connects to the plane, and so on and so forth, to use these to predict when the plane leaves. And this is the corner problem of that. You would like to do that, but you don't have data. You actually have no idea of when the fueler comes to every turnaround, or when the caterer comes to every turnaround. And you would say maybe you can solve this particular problem with some IoT system, but it's much more complex than that, because usually there is also a lot of actions which are done by humans. So you need to understand what is happening to the plane, which is done by humans, which makes all use of these IoT systems much, much, much more complex, because you essentially want to understand something from the behavior of humans. And this is the layer which we solve with Assaia. So essentially what we do, we install a single camera at the terminal building, which looks at the airport, at the specific gate of the airport, and it looks at the plane which is there. So yeah, and then based on what it sees, it can accurately detect timestamps of different events which occur during the turnaround. And this is a perfect input for the pipeline I've just described, this one. So once you have the computer vision, which gives you timestamps, you can actually use it to have much, much better predictions of the future. And you can do proper optimization of your airport later on. This concept is very general. It applies to everything. For example, if you have a classical example of self-driving car, it's the same. It's exactly the same. You use cameras on the self-driving car to understand what's happening around you. You use your predictive mechanisms to understand what will happen on the road in 5 seconds from now, and you optimize your decisions to take the best decision within the scope of information you have. So this is an example of industrial application. The goal is not to explain how Assaia works. If you're interested, I'm very happy to explain it to you at any time. This is my personal child, so I can talk about it forever. But I think you came here to get inspired on a general scope. So maybe we stop this and just go for different applications of computer vision. Because what I've also realized is that many people, when think of computer vision, they think, okay, there is quality control, there is self-driving, there is maybe a couple of more applications, but they don't really realize how wide the field is. So let me just inspire you with a couple of examples. So first is fashion. So we all maybe have heard that it would be a cool idea to, you know, take a picture of the dress and get the same dress on some platform when you buy your clothing. So this was cool several years ago. Now computer vision is talking about the concept called visual question answering, where you can not only say, okay, I want a dress that looks like that, but you can say, hey, this is a nice dress, but do you have something like that with stripes? And then you will get a dress with stripes. This is completely amazing, and this is really, really, really nice, because in the end, it allows humans to use no tools, to have a very simple interface, which is essentially just their natural language, to get the results they want. This is really mind-blowing, because in the end, it's exactly how you talk to your friends when you discuss clothing. This is super, super interesting. So this is what is already happening nowadays. Face forensics is completely different, but also a very exciting topic. So everyone has heard about, for example, deepfakes, which make you look like as another person. So this is already a product of computer vision, which produced a problem on its own term. So now you have to be able to identify whether the person talking to you is actually a person or is a fake person. The same also goes to some security applications. For example, if I unlock my phone with a face, it has to identify if it's actually me or if it's some kind of 3D avatar or a mask or a dead person, if you go to the extreme. So you have to apply a lot of research in face forensics to make sure that what you see in the image is what is actually presented in this image. A very exciting topic. Sports is a classical example for computer vision with a lot of unexpected turns. So of course you would say that the most obvious application for computer vision in sports is something which you see on the bottom left. So you detect different soccer players and you try to understand their strategy and so on. And this, of course, brings already a huge value. But there is a lot of other applications. For example, in the picture to the right, you have a paper which tries to detect groups of spectators which came together. It's very interesting because usually people who come together, the group, they show some behavior that they share, and you can actually identify them as a separate group, which is very interesting for retail and marketing opportunities. And it's not very directly to sport, but the point of that is that you can find so many unexpected applications that it is just really mind-blowing. Image enhancement is something which is more classical because computer vision is essentially about image processing. So in this example, the authors of the paper take some underwater imagery and make it look nice, which is essentially a physically impossible problem to take proper in-water images because the water is just not transparent enough. But they get so good results that they can make beautiful 3D coral reef reconstructions similar to the one I show to the right of this slide. Security. Not only detecting guys that are coming to your door, but for example, drone detections. Drones are super tiny, so maybe a radar will not see it. But if you can optically see a drone, then you can train a computer vision system to do that. Agriculture is huge. You want to understand what's happening to your field, where the crops have already come out, where the plants are healthy, where they're not. And if your farm is large enough, it's very, very difficult to do it. So what people do is they fly an airborne little plane, so they to collect these airborne pictures of their fields, and then they can get a lot of different value out of that about the status of their crops. So usually you don't use the standard camera like an iPhone has, which just can capture red, green, and blue channels, but you also use this NIR channel, which is near infrared, because for some properties which are not to be discussed in this presentation, this helps to understand more about the health of the plant. Retail, very classical example for computer vision. You know, everyone has heard about these shops which work without cashier. There is a couple of problems and challenges there. And one of the main challenges from the research point of view is to understand what exactly does the customer have. Because as we discussed, it's very easy to distinguish a cat from a dog, or maybe a beer from chips. But what happens if you have 100 different types of chips, which all look similar, but you still need to understand the price? So this is something which is challenging in retail currently, but there is a lot of research there. Or just as in the image to the left, you have densely packed scenes. So you have a lot of objects and you need to get a precise count. So this is something which I think is almost tackled now, but it's still a very interesting field of computer vision research. The last but not the least one, documents. So everyone knows that documents is a thing of the past and you need to digitize them all and you're done. But the interesting thing is that you're not done, because the point is not to have a digital version of the document, but the point is to get the information out of the document. And the proposed methods that I discuss currently is doing some kind of dialogue with documents. So for example, in the letter in the middle, you can just ask how old is the sender, and the machine which has first scanned the document, but also analyzed it from natural language point of view, has identified that the sender is 26 years old. And this is completely interesting. And what I really like about this documents application is that you would think that the field of document processing is shrinking because everything goes digital. But in the end, it's just growing because people still create a lot of documents, but you still, and there's more and more and more of them, but you need to have a proper system which can actually get the value out. I think that was enough of examples. I firmly believe so, but we can give some more in the Q&A section. I would like to spend the last couple of minutes talking about the future outlook for computer vision. So needless to say, it's a research field which is very active now. There is a lot of industrial interest in that. So there is a lot of research money coming in. And experiments are rather cheap to do, so there is a lot of development, you know, on neural networks just becoming more efficient, more precise, and cheap. So this is what's happening all the time, and that will continue going like that in the future. What is also interesting is that, as we have briefly discussed in the beginning, one of the cornerstone problems of computer vision is amounts of data you need to generate. Imagine a self-driving car. So essentially to have a perfectly self-driving car, you have to have a car which has driven an infinitely long route. So essentially you need to collect all the visual data which is possible in the universe, which is of course not happening in reality, because you have only a limited amount of self-driving cars which only drive a limited amount of hours and so on. So there is a lot of research which tries to tackle this problem, and with different ways. For example, one of the ways of doing that is doing simulations. So this is the picture on the bottom left. So you can make virtual cities. And once you have a virtual city, you can just run infinite simulations of what will happen there. You just have little cars which kind of follow some stupid rules and just drive on the streets. And you can put your virtual cameras anywhere, understand how it works, and just collect further and further training data for your system, which, however, comes for free because it just happens within the computer, and you actually don't need to put any hardware on actual cameras. So this is more like practical approach to self-supervised learning, to the process, which means that the neural network learns on its own. You also have some more, mathematical kind of tricks to make sure you squeeze more out of the data you have. For example, in the image to the right, you take an image and then you you disembowel it into these 9 particles, like a little puzzle, and then you want to solve it back together. And the only purpose of doing this seemingly useless task is to reuse the data to train your neural network to solve more complex problems, so that in the end you have a smarter neural network which essentially produces better results with no more data. So there is a lot of research there, and I don't want to go into details there because it's not that important. The only thing I wanted to say is that it looks like in the future we will see a significant reduction in the amount of data we need to use to train the machine learning systems, which is absolutely great. We know that computer vision systems and machine learning systems in general are awesome already. I'm totally in love with them. And just imagine how the world would look if they're the same, but they come at much cheaper cost, because essentially you don't need to collect the data for that. So this is what the future is preparing for us, and I'm personally very much looking to this future. Time for another takeaways. I think this is more the takeaways for the whole presentation. Jan Willem, do you want to summarize? You're on mute, I'm afraid.
Yes, correct. Thanks a lot for, it was very interesting what you just shared. To summarize a little bit the entire presentation, but especially the last part, is that the major bottleneck for AI over the last years, as I already said before, was the lack of sufficient training data. However, this in the future, as we just learned, can be done by self-learning. But still, although it takes a lot of data, AI was able to transform many application areas to a much higher level of efficiency and effectiveness. And due to new research, due to further research, and due to the things that are yet to come, this bottleneck is also about to be further reduced through, for example, the usage of simulations or self-supervised learning. And once this has happened, this will further turbocharge the quality and the breadth of AI solutions. So I guess the next 5 to 10 years will be a very, very interesting time to watch and see what will be possible in this time frame.
Yeah, I totally agree to you, Jan Willem. And what I also wanted to add is that AI is really broad. Computer vision is really broad. It's not only about self-driving and putting some cameras on the aircraft or airport. There's so many applications. It's unimaginary, and this is what makes it so cool. It's not like one little field which is only needed in some specific area. This is something which almost any process has some relation to, and this is what makes it so exciting. Great. Thank you very much for listening to my rather unstructured talk. Let's bring some structure and close the gaps by answering some questions.
Yes, please.
So Jan Willem, you would moderate it, right?
Correct. Please feel free to either post them via the question and answers part, or if you are bold enough, you can also raise your hand and I will let you speak. Now there's one question. So to get beyond an accuracy of, let's say, 90%, I can imagine that it is required to detect where the system is going wrong, i.e., where is my solution coming from, to improve it. That might prove hard with a more or less black box algorithm. How do you approach this at Assaia? Also, how do you generate trust in solutions, crucial especially in the aviation industry, since it is hard to trace and explain how the DL model arrived at the solution? So I think, Max, you're going to take that. You're on mute.
I'm not sure if I'm the most qualified guy to answer this question, but I think it highlights another very important attribute. If you look at, we want to apply AI to a certain problem, right? AI is inherently statistics, so it will not give you like an algorithm, a mechanic solution for any type of input. It will give you a solution and it will attach a probability or confidence value to it. So it's important if you want to have a system that, you know, decides over life and death, that in 10 billion out of 10 billion cases has to yield the right result, AI is not the right tool, which also makes it difficult, for example, to apply AI to, let's say, visual inspection tasks where you need to screen 1 billion screws per day. It will have most likely a much worse performance than a vision algorithm. How are we tackling this in Assaia, Nikolay?
So yes. So what Max said is generally very, very right. You cannot, as everyone knows, you cannot really look inside the AI and understand why the judgment was made. But the good news is that you can always understand how good your system is. So the classical approach is that you split your system into, you split your data set into training and testing. So you train the system on one data, and then you run it on the data the system has never seen. And this is the way you essentially get unbiased understanding of how well your system performs. So this is the fundamental test you use for AI. And in our particular case, you would prefer running it on a monthly basis because, for example, you have a camera which looks outdoors, and a lot of things change outdoors. For example, seasons change. For example, sun level changes with the time. I mean, it's the same as seasons change, but it's a bit different observation. So you need to make sure that your system actually works in all the times. So once you do these tests, I would say you can get pretty high confidence for the system working. However, you can do, of course, other tests. So for example, you can apply some common sense. For example, you say every plane turnaround, I need to see a fueling car. So we, for example, have this as well. And in the beginning, when the system was not working properly, we would have these manual tests. So every time there is no fueler detection on a turnaround, we will get an internal note saying, hey, could you please check this? Something potentially went wrong. So you don't really know the timestamp of the fueler, but you know it should come at some point. So by just doing some meta logic tests, saying it should come at some point, making sure, like if this test fails, you usually have a problem. You have to check a look. But the ultimate test is just looking at the data the algorithm has never seen.
I think what we learned from our engagements with customers is that it's actually not so important for the use cases that we are pursuing. It's actually not so important for the customer to have 100% correct data all the time. It's important for the customer, much more important for the customer to understand if Assaia generates a certain data point, how reliable is that observation, is that data point? So that's why we're providing with every data point a confidence value. And many of our customers are just eliminating any data point that is below, you know, let's say 75%, so 0.75. Since our average confidence is around, Nikolay, what would you say is our mean confidence value?
I would
roughly?
say 95% or something.
0.95. Cutting this off gives you know a sufficient solution for our customers. Yeah.
What I also wanted to highlight is that usually computer vision systems, even if the machine learning is perfect, still cannot capture all the data. For example, if you're a self-driving car and there is a person just in front of the self-driving car, you cannot see through this person. So anything which works with computer vision output should assume that your data is not complete. And this is not because computer vision is not perfect, it's just because life is like that.
I want to point out also another direction, it's so-called active learning. So at the moment, the Assaia solutions are producing some confidence on their predictions. So we can, from time to time, take exactly those predictions that are of low confidence and use some human to provide some labels. And then we can introduce in the training process and benefit from this kind of borderline cases to further improve the models that we are using. So this is like an active circle to improve the models.
Yeah. So what we're considering is, you know, for example, tapping into ACARS data as well. This would allow us to plausibilize certain events that we're seeing. If we see a fueling truck being parked, the hose being attached, that's everything we can. These are examples for things we can capture very easily. Then we could use the ACARS sensor data. ACARS is a system built into the aircraft that that sends the sensor data via radio waves. We could, in theory, wait for this signal from the sensor to appear on, the radio channel, and thus plausibilize what we're seeing visually. So that would be another crutch or improvement to the system.
All right. Thank you, guys. Any further questions from anyone?
I have a question for Max. Can you quantify the value Apron AI can provide to the industry? Is there anything behind it?
So that's interesting. We're 2 years in, and we still haven't found, the final answer to that. We're seeing a lot of inefficiencies on the air side of airports and all the processes that are happening there. And a major reason for this is that the data availability is very sparse for airside processes, especially around the turnaround process. So, if we look at how much damage create delays per annum, and if you assume just the Eurocontrol standard figures, which are I think 130 euros per delay minute, depending on which statistic you look at, that alone sums up to like $20 billion per year, right? Obviously, I'm not claiming that we can eliminate all of this $20 billion, but it gives a rough order of magnitude. And overall, if we then add all the accidents that are happening airside that are preventable, if you have the right data, if you know where each object is positioned on the apron and tarmac, you're looking at another maybe $50 billion. It's hard to get reliable figures on that. So overall, I think that the potential is huge. Yeah.
All right. Thanks a lot, Max. So I think we can still take one more question if anyone has any additional questions. 3, 2, 1. Okay. Then I think I will hand over to Max for just some closing remarks and thoughts.
Cool. Thank you. Thank you, Jan-Willem. So I hope this was worthwhile for you. Again, the idea was to spark your imagination, right? With regards to which level of AI, which layer of AI should be ours from the point of view of your business. Where can we apply AI and where is AI totally unsuitable? And I really hope that, you take some new ideas away from this session. We are always looking for partners to actually make sure that we can translate the data that we generate and the outputs that some of our algorithms generate into ultimate value for the customer. And the gap there really is the customer needs to change operational processes. And so if you're interested in working together, just fire an email in my direction, and we're going to be in touch, and we can look together at how we can eliminate all man-made delays from the global air traffic system over the next 10 years.
Thanks a lot, Max. Yes, I think that basically concludes our webinar. From my perspective, I would like to thank you again for your time. As Max said, I hope it was valuable, or we were able to share some valuable insights and it was worthwhile. If it was, we are happy for some positive feedback. If it wasn't, we are even more eager to receive some constructive criticism. And in general, we are currently also thinking about having some other webinars that will dig a little bit deeper into certain specific application areas, probably primarily in the field where we are simply most knowledgeable, which is the aviation field. So yes, please feel free to send us any form of feedback or also suggestions for a topic that you might find interesting. And with this, I thank you all. I wish you a very nice rest of the day, a very nice rest of the week. Stay safe and hopefully see you next time again.
Thank you very much also from my side. I just wanted to say, if you have any questions about AI, I'm very happy to answer them. So just write to Jan-Willem and he will forward it to me.
or
Correct.
to Max.
All right.
Cool. Take care. Thank you so much.
Thank you. Bye-bye.
Yeah,
Bye-bye.
goodbye.